Do you want to easily win $1 million? Well, lucky you, I have the solution. Simply answer to the question, is P equal to NP? But first, what exactly is NP and why it is, in my opinion, one of the worst ways of earning $1 million? In the last videos, we focused on Turing machines that take an input X and that always output the same thing. That is, in decision problems, either yes or no. And this kind of behavior that only maps one input to one output is what we call a deterministic process. What if now we break this property and that we allow what we call non-determinism, meaning that for some inputs, you can have different outputs. And how much power does this add to your process? That everything was just your output. And so, first of all, let's define what exactly is a function that is non-deterministic. If we have, for example, a function f that maps bits, so just 0, 1 to 0, 1, how to make it non-deterministic? Well, for example, we can say that f of 0 is simply equal to 0, and that f of 1 could be equal to 0 or 1. We don't know in advance. It could be anything. It depends on what happens in the run. It could be something close to what we call random runs. That, for example, at random, you will either have 0 or 1. But here, we don't talk a lot about randomness because we don't have like a probability that you will choose 0 or 1. We just say that either of those can happen and that we don't know in advance. And so we will rather talk about non-determinism than just probabilistic process. And so just as a drawing, if you have here 0, 1, 0, 1, well, a deterministic process will always map an input to something, just one arrow going from each input. But here we have 0 to 0, this thing is deterministic, but 1 could be mapped either to 0 or to 1. Now, instead of just mapping an input space to an output space, we will map an input space to the subsets of, we write often, to the subsets of the output space. Because, for example, here, the output of f of 1 is not 0, is not 1, it's both of them. And often the output of what we call a non-deterministic function is not the output of the single path, but all the possible outputs that you can have. And now, what if you add this property to the transition function of your Turing machine? We know that a Turing machine maps state, any state Si, to another state Sj of the Turing machine and of the tape. But what if now, instead of just mapping it to one state, we don't map it to a set of states? And so how this would affect our problem? Well, now, instead of just having x that has an input state and that we call transition function, and then we call transition function, and then we do so until we arrive to m of x. And so this is basically the steps that our Turing machine will take. So now, if the transition function is non-deterministic, well, at each step, you will have different possibilities. So here, you would call at the first time the transition function, and you could have two different outputs. And the same like this. You can continue like this, why not 3 different, and so on, until you just have at the end a bunch of different possible outputs. So a bunch of 1, 0, 1, 1, 0. And so this is what we call a non-deterministic Turing machine. It's a machine that runs in some time and that has this power of being non-deterministic. But how to use this power? How to extract information from this output string? Well, the idea is that each single path here can be encoded by a string y that encodes what choice you make. Let's take as an example the function that we have, that 0 is mapped to 0 and 1 is mapped to, at the same time, 0 and 1. Well, if we add a variable that tells you which is chosen, because we don't know in advance what will be chosen between 0 and 1. If we have a variable that tells you in advance what is chosen, well, you can make this function deterministic. For example, if instead of just having x, you have y here, then you can say that f0, 0 is equal to 0, and f0, 1 is also equal to 0, because here all the choices lead to 0. But now, what if you have f1, 0? Then you could say that it maps to the first output, and so this is equal to 0. And in the same way, we could have that f11 is equal to 1, because it maps to the second state. And so here, in a more general case, we can say that this y here will encode every possible path that you can have. Here, for example, it says that you take the first one, so here maybe it can be the bit 0, and then it can take also the first one, maybe then it can take the third one, and maybe then, I don't know, the first one again, and so on. And this string here will encode what choices are made. And introducing this path variable will allow us to define what exactly is NP. And so for the picture, we have that we have an input X that has a lot of different paths. And all of this is the output M of X. And if we want to extract information, we will use this, let's say, deterministic function that uses a new variable here that is not known in advance, the path variable. And so for each single output, you would have, let's say, this is mx of y1. Here it could be mx and y2. And here it could be mx of some ym, for example. And so now, to know which is the value of each single path, you have a variable that defines the input and another one that defines how the path is created. And now, using this way of seeing things, let's already define what is exactly the class NP. Again, as a reminder, we know that when you pass an input to your deterministic Turing machine that we'll call a DTM, but often we'll just call a normal TM, it will just lead a single computation, and then it will give you the output M of X that will either be 0 or 1 and will be the output of your computation. But now, let's say that you use a non-deterministic Turing machine. Well, here, a single input X will lead to a lot of different paths. And each path is encoded by a path variable. And so here, you will have M of X, Y1, here M of X, Y2, and here M of X, Y3. And so here, you will have a lot of different outcomes. And we say that the input X here is accepted if one of these paths gives 1. So if there exists one A such that this path leads to 1. And on the opposite, we say that the input X is rejected if for all the paths, the output will be always 0. This is how basically we define the class NP. But to be a bit more formal, we are talking about the class NP. And in NP, you will have the P that is basically polytime, just as the class P, because here you have at most poly X steps. And so here we want that each single path also has at most poly X steps. And now we have absolutely all the ingredients to formally define what is the class NP. So let's do it now. We say that a language L belongs to the class NP if there exists a polytime non-deterministic Turing machine that accept L. And more formally, it's the same as saying that there exists a polytime Turing machine, this time deterministic Turing machine, M, such that if the input X is in L, then it means that there is at least one path that will lead to the output yes. And on the opposite, if X is not in the language, then for all the different paths, well, your Turing machine will always output 0. And this is the definition of NP. And of course, here the size of Y is also at most polynomial in the size of X, because we want that this machine here runs in polytime. And so if it was bigger than a polynomial, just reading it will already break the polytime nature of the machine. And another way of seeing things is that Y will not be only the path, but we can see Y as being, let's say, a guess, that we have access to a Turing machine M, X, Y, and we only know the X, and it has the power to guess here the variable Y. And once the guess is made, well, it will be easy, or in other words, we can do it in polynomial time to check if indeed this is equal to 0 or to 1. And if at least one of these guesses leads to 1, then we accept. And if all the guesses lead to 0, we reject. And this is why often we call here y the witness or even the certificate. And maybe now everything seems a bit abstract, so let's already dive in our first example. One of the most important languages that belong to NP is the language SAT, that is basically defined as you have here a Boolean function, and you want to check if there is at least one assignment of variables that satisfies it. So this language is all the Boolean functions such that there exists one assignment of variables such that this leads to 1. And you can see that this already has the shape of what is something in NP. And first, what is a Boolean function? Well, a Boolean function is basically anything that you want with just variables that can be zeros and ones. So for example, you can have a Boolean function of some variable z, and z is, let's say, a vector of some bits. And here, this could be, for example, z1 and z2 or z3. And of course, here, if z3 is equal to 1, then everything will be equal to 1. So indeed, when you take this function, this belongs to SAT. But if you take something else, for example, phi of z that is equal to z3 and not z3, well, it will be impossible to always satisfy this, because if you set z3 to 1, then this will be equal to 1, but this will be equal to 0. And if you set z3 to 0, this will be equal to 1, and thus it will never be possible to have these two guys here that are equal to 1 at the same time. And so this doesn't belong to SAT. And what we did now is a perfect example of what is a language that is in NP. Because here you have that if your function here belongs to SAT, then there exists one certificate, one witness, or just one assignment, such that this function here is equal to 1. And on the other hand, if this doesn't belong to SAT, then for all the possible assignments, then your function will be equal to 0. And if we look a bit differently in our definition of what is exactly NP, this could be the input x, this could be our witness, and this process here of checking if the given Boolean function is satisfied by this certificate is your polytime Turing machine here. And we often say that this is a verifier, so often we don't write M here, but we write V for verifier. And so we say often that the languages in NP are easy to verify, but difficult to solve. Because we will see later that we don't know if NP is equal to P, but we think that NP is way more difficult than P. And so we often say that when a problem is not known to be in P, we say that it is hard or difficult. And when a problem is known to be inside of P, well, this is easy. And indeed here, if you give a witness to your verifier, if you say, okay, can you check if this witness, if this path leads to 1 or 0, well, your verifier will say, yes, of course, it's easy to do, I will do it in polytime. But if you just give the input x, or just a Boolean function, and you ask, is my Boolean function satisfiable by some Boolean assignment? Here, it's really difficult to know. And actually, it's the heart of the question, is P equal to NP? And the most naive way would be to look at all the different possible assignments. And if you have, let's say, n variables, then you will have 2 power n assignments. And this is extremely long. This is exponential in the input size, and it's way, way bigger than just polynomial in the input size. And so far, we don't know how to do it faster. The fastest way that we know is indeed using exponential time. And so, okay, it's a bit difficult. And the first time I saw what is exactly the class NP, I had to take some time to really understand what is it. So let's just make a last recap. First, what is the class P? Well, we say that L is in P if there exists a polytime Turing machine such that if x is in L, then m of x is equal to 1, and if x is not in L, then m of x is equal to 0. And in a very similar way, we said that L belongs to NP if there exists a polytime Turing machine such that if x belongs to L, then there exists at least one witness, one certificate, one path, such that your Turing machine mxy is equal to 1. So one of the paths leads to 1. And it's not in L if for all the variables, for all the path variables, or for all the witnesses, well, m of x1 is equal to 0. And so we can see that the definitions here are really similar, with the exception here that we introduce what we call the new variable here. That will be something that we don't know in advance, that will kind of be the variable that where the non-determinism lies. We never know in advance what is this y, and often we want to find this y, the y that will satisfy, or to prove that none of the y's will satisfy our problem. And often we call this m here a verifier, because just given a guess that we can give to it, it can easily verify. And so it's easy to verify, but in practice, a general problem, it's difficult to really find the solution, but easy to verify. And also we defined P as simply being the union over all the problems that can be solved in polynomial time. As simple as that. And in a similar way, we can also say that NP, and each time that we will put n before anything which is a class, a circuit, a Turing machine, it means non-determinism. And so it's basically the union over all problems that can be solved in non-deterministic time. When I talk about the class n time, it's the fact that you can have an input here, and you can have a lot of different paths, and as long as each of the paths take polynomial time, well, this process is in the class n time polynomial. And so this is how we define it in practice, P and NP. And this power, of course, of non-determinism cannot be done in practice. And we can think why we want to study this. And the answer is simple. It's because there are a lot of natural problems that lie in this class NP. For example, the problem that is SAT, the satisfiability problem, or even other graph problems such as the vertex cover or the set cover problem. And we don't know if these problems are easy. And if one day we can prove that P is equal to NP, we will just prove that these problems are easy to solve, but it's really, really unlikely. And since years and years, we've been trying to separate these classes, but it's really difficult. But to see this a bit better, let's dive into our last part and explore the relationship between P and NP. And so the first thing that we can notice is that obviously the class P is inside of NP. Each time that we discover a new class, it's very interesting to try to see whether it is a subclass of another class or even something that is bigger than some other class. For example, here NP is bigger than P in the sense that B is contained in NP, but we don't know if it's strictly bigger. This is the question. And so, how to prove this? How to see this? Well, to do so, we can just take any language that belongs to P, and we can try to prove that it also belongs to NP. And so we need to, let's say, construct a verifier that will have this shape of if x is equal to L or not equal to L, then there exists some y that has a size polynomial in x such that the verifier xy is equal to 1. And if it's not in L, then for all the different variables, then this will always lead 0. We need to find a way to write our original problem into such a problem. And it seems really easy because just this thing adds way more power than just having not variables here and simply having this, that is the definition of P. But let's still do it. We can just say that here we have our Turing machine M that accepts L. That is like if x is in L, then m of x is equal to 1. And if x is not in L, then m of x is equal to 0. And m, of course, runs in polytime. So how to use this Turing machine M to create, let's say, a verifier here. And a very easy way to do so is just to ignore any variable here. So for example, you could say that m prime that accepts the input x and y will just output m of x without dealing with y. And so here, if x is in L, then there exists indeed y such that m prime of x of y is equal to 1. And actually, because we don't care about the y here, well, actually for all the y's, this is equal to 1. And on the same way, if x is not in L, then no matter the y that we'll choose, because we will always ignore it, so for all the y's, m prime of x and y will simply be equal to mx, and because x is not in L, well, m of x will be equal to 0. And this is how we prove that p is indeed equal to np. And this part is really obvious. And now I challenge you to do the other side, which is proving that np is indeed in P. But the thing is that we don't know. We don't know if this is true. And we think that this is wrong. This is not true. Because we are basically sure that the picture is that you have the class NP and here you have the class P. But we don't know. We don't know to prove that there is something that lies here and that doesn't lie here. And if one day we can prove that there exists a language that belongs to NP but that is not in P, then we'll succeed. But this way of proving is really, really difficult. So complexity theorists have tried to do this for years and years, and still, even if the best minds in this world try to solve this problem, still we don't know how to prove it. Even if we are really convinced, we don't know how to formally prove this result. And who knows, maybe it's because just NP is just the same thing as P. But this seems really unlikely, because the thing is that NP adds a lot of power, because here when you work in P, you just have a single path from x to mx. And so here in NP, you could do exponentially different results, because if you have a path variable here that is polysize in x, then there are 2 power polysize of x different outputs. And so we could think that basically the things that are in NP could use exponential resources. And so thinking about this, would say just, yeah, of course, NP has exponentially more power than P, and so this thing would be really, really stronger. But no, this is not as easy as that, because it doesn't have all these resources, because it could if actually all these things were computed in parallel. So if this could communicate with this, and this with that, and this with this, indeed, this would be simply the class exp, which is the class of problems that are solved in exponential time. But here, all the paths are individual and don't talk with each other. They just do their thing. And at the end, you have a 0 here, 1, 0, 0, 0. And this means that the variable here is accepted, but they cannot communicate between them. It's really independent. And this is why we don't talk about parallel computation. And we have a class for problems that can be solved in parallel. But here, it's not about this. It's about non-determinism. It's about not knowing the result in advance for not assigned variables in advance y. And so this idea of trying to know how much power is added with this kind of process to the simple deterministic process here, we don't know. It seems that still it's not exponential, but what if it is exponential? Because if we prove that SAT requires at least 2 omega n, so at least 2 power something times n steps to be solved, well, it will mean that indeed NP has exponentially more power than P. But we still don't know. We think that, but we are not sure. And this is really, really mysterious about this class. But the good thing, or the bad thing, is that it's not the only mystery about computational complexity. There are a lot more. And in the next video, we will introduce the, let's say, evil twin of this class NP, the class co-NP. That is basically NP, but in a reversed way. And we don't know if co-NP is equal to NP. And this mysterious property of NP is something really common in a lot of different classes that we will see later. And it's really interesting, but also so frustrating to not know how to prove these things. And these results that are really difficult to prove, we have a bunch of them in complexity theory. But let's keep it for the next videos. For now, I'm done, and see you for the next video.